Okay. All right, welcome back, everybody. So we're going to go to the last piece of the trajectory optimization sort of segment. And actually, I motivated it already. And let me motivate it again here with the perching example. Okay, so we remember we were doing trajectory optimization for perching as an example. I wrote a small direct collocation code. It does, it does a little optimization. It finds a trajectory that satisfies the dynamics and lands exactly on the perch, right? And then if I take the trajectory back, which if I use direct collocation, remember that I have an explicit piecewise cubic polynomial representation of x over time, and I have a piecewise linear u over time. Okay, so if I just start a new simulation, and the input port of my dynamical system, I just read off u of t from that trajectory. That's what I'm calling the open loop simulation, right? So I'm just playing the tape of u's. It's not looking at the state of the plane it over. It's just as a function of time, it's going to decide what u is. It plays it out, right? And what happens is that the blue is our nicely designed trajectory. The orange is the trajectory that the airplane actually follows, and it misses the perch, right? Yeah?
Is that not the same solver that did both? Like, why in simulation? I understand in real life. Why is it different in simulation?
Good. Yeah. So if I used exactly the same integration method, then I would expect it to up to any numerical quirks to be the same. But you're right. I think I said it more carefully last time. But so the direct collocation is using a particular third order accurate integration, and it's actually an acausal integrator. So the one I'm using in forward simulation is actually slightly different. And that's enough. Just a small difference in like using a Euler method here or a Runge-Kutta method here is enough to change that outcome. Yeah. Okay, and so what we can do today is try to stabilize that trajectory. So solving the relatively hard problem, I guess, of trying to find any trajectory that gets me through the reasons about the nonlinear dynamics and gets me to the perch, that's one problem. But after I have that, if I'm a little bit off and I just want to get back, that's relatively a much easier optimization problem. And in fact, we even have ways to use LQR to do that, which you saw a little bit of that in the iterative LQR problem set. And there was some good feedback on people like, I did the ILQR problem, but I don't know if I really understand ILQR. So hopefully by the end of this lecture, you'll understand that. Okay, and long story short, if you do LQR only on that, then not only does the nominal initial condition get to the perch, but even there's a range of initial conditions that just by running an LQR controller, okay, will stabilize that trajectory and get to the perch. Okay, the actual the actual hardware, we didn't actually make there's groups that have now made really cool like claw mechanisms so they can grab, and we actually collaborated a little with Mark Riccati, who had spines and we could like perch on a wall, those. But ours was just like a hook, right? And so the region where we had like our region that you had to hit in terms of state space was actually pretty small for it to sit there and hook on. If you used active claws, you could do a lot better. But we really wanted to be very close to the desired trajectory. And the orientation mattered for our hook and stuff too. Okay, so first part of the work here is to just understand how could we use LQR to do that. It's not that different than what you've seen before, but there's a couple of key ideas that have to get across. And the first of those is the idea of linearizing along a trajectory instead of linearizing around a point. Okay? So now you remember when I tried to talk about linearization actually capturing the dynamics well. I did the phase portrait of the pendulum. Right, and we linearized around the upright fixed point, and we saw that we got a nice, a pretty good approximation that was accurate in the vicinity of that point that we linearized around, right? No, this and like that, yeah. Okay, so the first question I want to ask you is first just, what would happen, so that was about linearizing around this point. What happens if I linearize, let's say, around that point? Okay, if I just did the exact same math I did before, but instead of choosing x nominal to be this upright fixed point, I chose this point. And one of the key differences here is that this was a fixed point, and this cannot be a fixed point because it's got non-zero velocity. Okay? So if you just do the exercise here and you say, okay, I've got, x dot equals f of x. Even if I have I'll do as if I have a torque input too, okay? I relied on, when I did my linearization, I said this is approximately f of x0, u0, plus partial f, partial x, approximated like this. This is my first order Taylor expansion. This is evaluated at x equals x0, u equals u0. Right, that was just my linearization, my first order Taylor approximation. And in the previous case, when this was a fixed point, then that, this thing became my A matrix, right? This thing became my B matrix. Everything looked fine and linear, but because I didn't have that term to worry about, right? So the first thing that happens if I linearize around this, and that is not a fixed point, because velocity is positive, so velocity is not zero, and therefore, and I know the first equation of that for any system is going to have, any second order system can't have a fixed point with a positive velocity. That means this term is not going to go to zero, and I'm going to have something else to deal with. But remember, we worked in the error coordinates already because we wanted to be linear in this. So we already defined x bar so we're close. If we want to think about this as x0 dot, okay, we're very close to having something that works. And really the only thing that we have to do to make this consistent, and let me say it straight out and then we'll make sure we understand it, is I have to think about x0 and u0 not being a point anymore because a point can't have a velocity, right? I need to think about this thing that is now a trajectory, okay? So x0 is now x0 of t, u0 is now u0 of t, okay? And now taking the time derivative of x0 sort of makes sense. That's just x dot 0 t. I can just add my t's here everywhere. And that makes the math work out, right? Notice that at each time here, I might actually, I'm going to be potentially at a different x0. I'll have a different A matrix and B matrix. So I now have a time-varying linearization. Okay, so that's the way the Taylor approximation math looks. What does it mean on my picture? I've got a very unpleasant thing there, okay? So when I ask the question, what happens if you linearize around here, right? If you just look at the A and B matrices, then what you'll see is you'll see a beautiful local approximation of the dynamics, right? It does the right thing. It will get worse as you get farther from that linearization, but it's correct. The only problem is you can't stay there because it's got the first order Taylor approximation is not zero, predicting zero when you're at that point. It's saying you're going to move that way. Okay, so it's not. So if you don't get a linear system when you get an affine system because of this. If you were to try to stay there, the way you get linear again is by saying I'm going to have a linearization that moves along the trajectory. Okay, and along that trajectory, I can have an error dynamics which is linear, time-varying linear. Okay, so at time 3 or something, I've got a linear system that's over here. I've got another, time 5, I've got one over here. Time 6, I've got another one that's over here. Okay? That's the idea of the time-varying linearization. Again, it can capture things extremely well, even the nonlinear dynamics. A time-varying linear system is actually very general, right? It can describe very nonlinear systems, potentially, okay, but it'll describe them well locally. And honestly, the perching, I used to, when I started as a faculty, I was like, old people did linear control. I should probably not say that, but old people did linear control. The new world is nonlinear, right? The world is really nonlinear. We need to invent new techniques for nonlinear control, whatever. And it was actually the perching project where I first realized how good linear control was, and I had to, eat my hat. So, so that Joe throwing that plane, right? I watched linear feedback control do highly non-trivial things to stabilize and land on the perch, right? So if the nominal trajectory kind of went like this, sometimes it would if you came in too fast, it would actually tilt up sooner to bleed off more energy and land on the perch, right? If it was coming in too slow, it would dip down to pick up energy and come back. Things that I would think of as being very nonlinear, right? But this all came from just the local linearization along that trajectory. Of course, only in some regime. It couldn't do too much of that because at some point the dynamics would change over the state space. Okay, but it was capable of doing very sophisticated reasoning over that trajectory. Does that idea sort of make sense? Yeah.
I guess, is it significant that we're defining the evolution of our matrices in terms of time rather than as a function of state?
Yes. So that's a good question. So is it significant that we're choosing to write this as a function of time? So where does the time come in here, right? So I now have time explicit here, right? So just by evaluating my dynamics at different times, it's natural. I didn't make any, I didn't make any particular choice to do this. It's just natural. I would say that linearization is a function of time because it depends on time in that way, right? But let's just say as a computational object, if I had something that was A of x, or A of x bar, then that would not be a linear dynamical system. Right? This is a time-varying linear system, and so we can do actually more with it than if it was a state-dependent A there. There are ways to try to work with things that are state-dependent in some weak ways, but really that jumps into a more nonlinear class of objects. Yeah?
When we're linearizing on this trajectory, even though we're making linear approximations at each point, we're not necessarily diverging from, like, as this time-varying system moves, it's not necessarily diverging, but locally it might diverge if you try to use that linearization and extend it.
Let me say that back to you. So what we would like to do when we apply LQR would be to say that x bar is going to go to 0, right? Well, our goal here is that x bar, which is a function of time, goes to 0, and that would imply that x of t goes to x nominal of t, right? But this is very much on a clock. That's one. That might be the other part of what you're asking, right? So one of the things that we'll look at more. But if I were to, start my perching trajectory, and the clock starts there, right? If I were to somehow stop, like hold the plane for a second and then go, it's going to try to catch up with the original time, right? It's not smart enough to say, oh, well, we have versions that are smart enough, but they're more work to get right. To say, find the closest point on the trajectory and then use that linearization. This is a linearization that's just racing ahead, okay? And at every time, I'm doing my best to get back to that linearization in time. Yeah?
Does that mean it's not robust to disturbances in that case?
So if you were to, it is robust to disturbances, but one thing that you might think it would be more robust than it is, if to perturbations in time, are not free. They're just as bad. Like sort of perturbations along the trajectory are in some sense just as bad as perturbations off the trajectory. That's the thing that's surprising. You might think if I pushed you right along the trajectory, all should be good, right? But actually, it's just as bad as being pushed off.
I'm not sure whether this makes sense, but why do we linearize around our desired trajectory instead of like where we actually are?
Okay. So there's a question. So let's say I got knocked off. Why don't I immediately linearize around the trajectory, the place where I am, instead of going back?
Wouldn't that always be more accurate?
So that we'll get back to that when we talk about model predictive control versions of this, which is more like, because you have to solve some trajectory optimization problem again or something, right? This is a nice way to a priori. Remember the same way I said I was afraid to run trajectory optimization on the fly? Right, I can pre-compute this funnel library, and then know that it's good, and it actually has a simple mathematical form. I could verify it. Going on the fly to linearize, it's a harder thing to analyze. Yeah.
On QR, question about convergence. On QR, we asymptotically converge to the desired location. Here, you're going to be on the perch in 2 seconds.
Okay, that's a good question. So he says, what about the convergence? What can we say about convergence? We have a finite time, and convergence is normally in time goes to infinity. That's good, but you're stealing my lecture. So I'm going to wait. If I don't answer that in a few minutes, I'm good. Then ask it again. But that's good, yeah.
It sounds like if you're trying to catch the trajectory that you anticipated,
yep.
the weighting that you give to position versus velocity is going to totally change what it does to catch up. Right?
That's true. That's true. The cost function will affect the way it tries to catch up. That's true.
I guess the funnel is size, like, is the funnel of constant radius?
We're going to understand that too. Yeah. You guys are awesome. I love all the questions, but I have prepared answers to some of these questions. That's great. Okay, so let's just think about how we work, how do we just make LQR work for the moving coordinate system, right? Really, this looks almost identical to what we had before, right? The major difference is the time, and perhaps that this object is defined over some finite trajectory, right? Like the Sava's question about it's not necessarily time from 0 to infinity, it's time over the duration of the trajectory. So what does that actually mean, right? So if our goal is to make the error dynamics go to 0, then we can write almost the same optimization. This is now, well, let me just say the time-varying LQR first. Okay. Turns out that I'm trying to find the min over some trajectory of some cost function x bar transpose qx bar plus u bar transpose ru bar. Okay, subject to x bar dot equals a of t x bar plus b of t u bar. Then the derivation we did before, if you just carry that t everywhere, is almost identical. Okay, if you write the HJB equation, you have the 0 equals min over u, L of x u plus partial x, f of x u. Now we're going to find that our cost to go function is going to be a function of time too, so we have an extra term like this, because we're going to be looking at j x star is an x. Maybe I won't write the x bar everywhere down here, okay? But every time I write x here, it's really just, I've switched to x bar here, okay? Now, j is also a function of time, and it's going to be, we're going to look for j's of that form. But because that's my guess at the quadratic form is a time-varying quadratic form, which I can verify through the Hamilton-Jacobi theorems, right? But if to take the full gradient, I have the time derivative j dot is partial j partial x times x dot plus the direct partial j partial t. And you can drop in q and r here. You can drop in a of t, b of t here. You can drop in s dot here. And it's all derived in the notes. But the point is that you're going to get a very familiar looking object out with one important difference. Right? So you remember we had before, in the time invariant case, we had 0 equals S A plus A transpose S minus S B R inverse B transpose S plus Q. Okay, this is the Riccati equation, the continuous time Riccati equation. Now, in the time varying case, we have just a few extra terms, but the object we get out is now a differential equation in S from exactly just running the exact same steps. We get an otherwise identical object, where now I just have t's everywhere. I can even make these time varying. I didn't do it here, but doesn't make anything harder actually either. This is called the Riccati differential equation. Okay, so the Hamilton-Jacobi Bellman sufficiency theorem, to satisfy that, I need to find some S which satisfies this now matrix differential equation. That's what the math tells us. Yes?
Since R is time varying and sort of arising from a process that we might not get to look into, or is R not time varying?
I left it as fixed. It can be time varying. That shouldn't hurt anything.
That answers it indirectly.
Yep. But R is always, even if it was time varying, it's under your control. That's your design parameter. Okay, so then to find a solution for this, we actually just pick an initial condition for S final, which there's a right answer for that, okay? And we just integrate the differential equation. Weirdly, we do it backwards in time, right? So the reason I left it as a negative over here, the differential equation, that comes naturally, but it's actually, you can differentiate an equation backwards in time. It's just the negative of the derivative forward in time, okay? So we actually have a final condition of what we know S is going to be at the final time, and we're going to just numerically integrate it back towards time equals 0, okay? That is just the math that comes out of the Hamilton-Jacobi, but I want us to understand it more intuitively, okay? So let's be a little bit more careful now about what's the interval that we're integrating the cost over. Okay, so if I said maybe it's from t0 to t final, if that's the finite now horizon that I'm going to optimize that over, then if I just used exactly this cost, then actually S at time final would be 0. The cost at time final, there's no time for any cost to accrue, so it would actually be 0. But it is common to add in an extra term which would say that X bar at T final, you could have a terminal cost if you want to add, some final conditions or whatever, and then S at T final becomes Q final. That would be my initial conditions for my cost to go, which is natural. The cost, if the cost at time final is this, then of course the cost to go is this. Instantaneously it has to be that. Okay, so for LQR, this was happening under the scenes. You just called LQR, A, B, Q, R, and it gave you S, and it was doing that by solving this equation. Now you say A, T, B, T, Q, and R, for instance, and you give it the final conditions, and it'll numerically integrate it, and it'll give you out S as a function of time, is what's happening behind the scenes. Okay? So let's just think about that object for a little bit. So it's kind of weird, right? This is the makings of the funnel, right? So we've already seen pictures of it in some sense. For the pendulum, I could, for the pendulum balancing at the top and my linearization here, I could draw my level sets of my LQR cost to go by looking at that S. This was, J star of X equals some constant, right? This was a level set, and I could draw the level sets of my cost to go function, right? And in the LQR sense, it was elongated nicely along the dynamics, right? The places that where the dynamics are pulling me in are going to have less. I can be farther away to obtain the same cost, right? The steeper eigenvalues of S, the larger eigenvalues of S are like this, and the smaller eigenvalues of S are like that. Okay. In the perching, the object, I'm drawing exactly the same thing. I've picked some sub-level sets. Now we're going to call them row of, J, X, T equals row of T. It's actually, I tend to use row for it, okay? And that's going to be at every time, it's going to look like an ellipse, okay? So that is an ellipse pulled backwards in time, and I can just plot it like that. And since this is just x bar st of x, the shape of that ellipse is based on the shape, the values of s, right? And in particular, the eigenvalues of s will tell you how big or small it is. Okay. Now, what's interesting is this differential equation, if you integrate it backwards in time, s can actually get bigger, but it can also get smaller. There's no immediate guarantee that s is only going to get more cost as you go back or anything like this, okay? This is an indefinite somehow, this side, the derivatives can be positive or negative. So let me try to sort of work through that in an example, okay? So let's do LQR for the Cartpole, okay? Time-varying LQR. So first I'll use the trajectory optimization we saw before to come up with a nominal trajectory. It looks like this, okay? So I've got a finite trajectory that came out of trajectory optimization. And if I were to start it from a different initial conditions, it might not get to the top, okay? So then I'm going to call finite horizon LQR, which is just this call in Drake. There's a finite horizon linear quadratic regulator, which takes it takes it through an options because there's so many different ways you could write it, but it takes your Q final, it takes your X0, U0, comes right out of the trajectory optimization. Okay, where did the solutions go? And now that stabilizes. So my blue was my nominal, my green is my actual, and even in feedback now, that's stable and gets to the top. So that's really the same thing I showed you for perching, but just the exact same code. Works for Acrobat, it works for Cartpole. I didn't even change the Q matrices. It's exactly the same, okay? But let me just plot it a slightly different way. So what I'm going to plot this time, I'm going to run exactly the same LQR design, okay? And this is from 0 to the time of the trajectory. And what I've plotted here is the largest eigenvalue of S. Some sense of like how big S is, okay? Or how steep it is, really, I should say, okay? If I were to pick a constant number, it would tell me how big that sublevel set is. And it goes up, it goes down, right? It's kind of an interesting object. So what would it mean if the eigenvalues of S get large around time 2? What does that mean? That means, say it, yeah? Our cost is definitely changing quickly, yeah? But it means if you're around that part of the trajectory, if you're only a little bit, if you have a large S, that means you're only a little bit away from the trajectory, you could incur a large cost. So that's kind of showing a place of high sensitivity. A small error in the trajectory at that point gets a large cost to go. That's exactly what that's saying. Now this is a Cartpole, so we should be able to think about that. Why is there something happening at time 2 for a Cartpole that makes that go like that, right? And here's as a hint here, right? Here's the angle of the pendulum over that same time interval, just from the nominal trajectory. Everybody's gesticulating. I think you're close, right? So that is, I don't know if you can read it from where you are, but that is at pi over 2. Yeah? Okay. So there's a particular place in the Cartpole, a particular set of states that look like this, right? When the pendulum is horizontal, okay, then remember the control authority we have is we have a force being applied here, and ultimately we're trying to stabilize a trajectory in both the cart but also the pendulum, okay? And that relies, when I'm down here, if I push the cart, it's going to move the pendulum. Okay? But the system is sort of singular instantaneously there. Nothing I can do with my actuator can affect the orientation of theta. Okay? So if you have a small error at that point in time, that's like where you're sensitive. Right? A small deviation there can cause big changes in your rollout. Okay, and you can see that by looking at the singular values, or the eigenvalues. It's a square matrix. Eigenvalues of the cost to go. Yeah?
Should we expect the largest singular value to be continuous, or could you have cases where sort of you hit a point where one singular value decreases, another increases, and you get sort of a corner?
I think it would be continuous, but maybe not smooth in that case, right?
Yeah.
So the question is, should we expect the largest singular value to be maybe smooth? I think you're right. You could probably have eigenvalues cross and have a non-smoothness there. S, as a function of time, you'd expect to be smooth. But the eigenvalue projection could be a different thing. Yeah?
In this case, what if this X bar was like a stochastic system, like AX plus B plus W?
Okay.
How would that affect the cost of
Okay. There's a magical thing. So we will actually cover stochastic control later in the semester. It turns out in the linear Gaussian case, if I made a linear Gaussian approximation, I added just a Gaussian noise here, it doesn't change, and you're doing expected cost, it actually doesn't change the answer. It's a weird, I mean, it changes the cost you'd expect to incur, but the control gains should be the same. That's a result we'll understand more carefully later, but yeah. So like the best and worst thing that ever happened to LQR was because that's why we have like people do state estimation in one part of the department and control in the other part of the department because of the separation principle and this invariance to noise and stuff like this. It's like magically good, but it's only true for linear Gaussian systems, and so we shouldn't have ever separated the departments. Yeah. Yeah. Oh, sorry.
So there will be no variance of noise in the cost of it?
We're looking at completely deterministic right now, and the only robustness we're asking for is in terms of initial conditions. That's kind of our surrogate for being robust to noise, is that you think about noise as changing my initial conditions. If I'm robust to initial conditions, and for a deterministic system, then I'd like to be, I say I'm robust. Yep.
So just to clarify what's happening here, it's still a fixed x naught and u naught for this one?
Yes. Yep. So I just linearized along a particular, the one I got out of trajectory optimization, the one I showed you. It just happened that x naught went through this sensitive place. And so when I plot the cost to go solution right at that point, S is big. Cool. Okay. So it turns out that this, the same way that LQR gave us this quadratic form around the fixed point that we could then use sums of squares, for instance, to find the region of attraction. There's a similar story. You can say that this thing is going to be a time-varying Lyapunov function. And I can talk about its reachability by looking at by using, for instance, sums of squares to certify that I stay inside the sub-level sets of my cost to go function. So let me just sort of tell you the basic mechanics of that. Okay. So let's just think about time-varying Lyapunov functions, but let me do it in two steps, because let's first just think about time-varying dynamics. Okay, so if I have x dot is now a function of time in addition to x, which is what's happening with my a of t, b of t, that's a time-varying dynamics. If I can find a v of x greater than 0 such that for all time v dot of x which is just partial v partial x f of t of x is less than 0 or less than or equal to 0, or depending whichever version you're trying to use, then of course that's like the simple case, right, where all of our old Lyapunov arguments still hold. You're just saying the Lyapunov conditions held for all time. So v is still a Lyapunov function in that case. And if you're thinking about writing a sums of squares problem, for instance, you've just picked up one more indeterminate. You're going to write for all t and for all x, I'd like this thing to be less than 0. But this is like almost no change to the sums of squares, as long as you're saying that, I have to find one v that's true for all time. If it was only defined from t0 to t final of some trajectory, you could use an S procedure to limit the domain of t. If you have now time-varying, you can have a richer parameterization if you allow for a time-varying Lyapunov function. Okay, so even if you have just this, you could still say, you could look for a time-varying Lyapunov function, saying that this, for all t, it's a positive function like this, and for all t, v dot of t of x, which is now the direct thing that we've done before, but there's also a term like this. If this is less than 0, then I still have some nice things that I can say. Right? If I have a property that even if v is changing as a function of time, if v dot, which includes the way v changes over time, is less than 0, then I know, for instance, if at time 0 my Lyapunov value was 3, I know it's going to always go down. Does that make sense? So I've got some function. It might be changing over time. That's fine. But if I can certify this condition, if I start, just like the mechanical energy, remember I said if I started with energy 3, then I know that I'll never have energy 5 later in time. Right? These conditions are still sufficient. Even if my definition of energy is changing over time, if I started with some level 3 and I satisfy these conditions, then I know I won't be higher than 3 ever in the future. So if I want to drag my definition of v through space towards a goal, but I certify these conditions everywhere, then I could say if I started inside some less than 3 over here, even if less than 3 moved, in order to satisfy this condition, it says that I'm still less than 3 for all time. You guys didn't love that. Okay? V is just a scalar quantity. This condition says that that scalar quantity can only go down. Right? And it's a more interesting thing to verify, to verify it for many times. But even if your function is moving over time, if that function is still going down, you can make a lot of those same statements. Okay, so in the perching example, for instance, or the Cartpole example, I have a function that starts being defined as 0 at the initial conditions and a small funnel, but it would be very large at the perch at time 0, right? And I'm going to move that function over time to get to the perch. In order to even stay at, like, if I just started at 3, let's say, and stay at 3, I have to move with my function in order to satisfy these conditions. Okay? So that tool allows you to make statements about reachability, for instance. If you want to say statements about reachability, for instance, you want to say something like, for all x at time 1 that are in some, I don't know, big set x1, I want to guarantee that at some later time x2, I'm definitely inside some other set x2. Which is a useful thing, right? So I'm saying in the perching, I have some region that's a small region around the perch. That would be my x2. I want to say when I get to time 2, I want to be inside that perch, that perching region. And I'm going to be able to try to construct that initial funnel, the x1, right? So that I can say, if I started in x1, I will get to x2. And a condition for doing that is finding a time-varying Lyapunov function, which is inside x2 at time 2, inside, outside x1 for time 1, and I can make that argument. Yes?
So to do that time-varying Lyapunov function, we can't have time-varying dynamics as well.
You can. So I wanted to just separate the two concerns, but the very natural thing is to just put them together. And then you can have time here also. Good. Thank you for asking that. Yeah, you absolutely can. In fact, it's most common to see these put together, in particular because of the time-varying linearization. Yeah. But time can enter in two ways, and they're both relatively easy to accommodate, although that becomes, an more interesting object to reason about. But it's an almost identical sums of squares program. Yes?
When it comes to linearizing around the trajectory, and we sort of do the same coordinate change, but we essentially put the point in trajectory as the origin and think about the moving frame, does that second condition become a lot easier to check because you don't have to build up the dvdt anymore?
Oh, sorry. So I still have that condition in this derivation. Sorry, so did you change this and get rid of that for me? Or
maybe I'm misunderstanding. Is the cost over there written in terms of the relative x bar coordinates, or?
Yes.
Oh, okay.
Yes. This is where I was like, I'm sorry, I should have maybe just carried the x bar everywhere. It seemed like a lot, but it's better to write it like that, I think. Geez, that was the only one I had to do? Yeah. I should have just done it. Sorry. Yeah. It just started feeling like a lot, This also feels like it's in the way, but it's kind of wired in. Hopefully that's better. Yeah.
The way I'm imagining this time-varying Lyapunov function is kind of like if you plot v over x, it's like a bowl that's moving over
Yes,
time.
exactly right. Exactly right.
But I guess this is something where if you're ahead in time, you're going to try and you're tailgating almost. And so is it ever useful, instead of it being a moving bowl, for it to be like a rut?
That's an amazing question. Okay, so just to say it back, right, so I think the picture you have is that we had a bowl around the fixed point in LQR. Now we have a bowl, that, a quadratic form that's just moving in time. So that goes back to you get behind in time. Your bowl kept moving, and so even if you stayed still, you would be going up the bowl, right? So why don't we have like a trough through time along the trajectory? If I knew how to, I would. I do kind of know how to. Like there's a way we can do it, but it's slightly more complicated. It turns out to be most important in my world when we were doing walking robots. So I was going to introduce it when we talked about walking robots. But there's a way to do a transverse, basically only linearize in the directions off the trajectory and have a whole trough. Okay, but there's more machinery to make that work, and it's actually not obvious that it should work, but it can be made to work. That's a great question, and that is exactly the right picture to have in your head. Okay, just a few subtle points about if you were to, in your project, start trying to compute these funnels or whatever. There's a couple interesting points that I can just make at this level of detail. We always have choices with Lyapunov. Are we asking for it to strictly decrease? Are we asking for it to be less than or equal to? We can talk about different forms of stability. We can even ask for a rate at which it decreases. Okay. One thing that comes in the practice of this is that it kind of goes back to that we chose a particular integration scheme for our trajectory, and it's probably not perfectly feasible trajectory. We have almost always the nominal trajectory that we're trying to stabilize to is an approximation of an accurate trajectory for the system. So if you actually ask for this to be strictly decreasing for all x around the trajectory, it will fail because of the numerical errors. There'll be places right next to the trajectory that once you start doing more symbolic, or more sums of squares kind of things, it will actually not be able to say yes all the way down to the trajectory. Is that kind of clear? Right? The true dynamics will funnel to some place, and it'll be a little bit off the numerical approximation of the trajectory. So in practice, we actually try to certify these conditions. For instance, where we would normally write v of x of t less than, let's say, rho of t implies v dot. Turns out the condition you want to check is rho dot of t. I'll draw that more carefully in a second. This can be a hard condition to satisfy all the way to 0. We end up saying something like this. Instead of going all the way to 0, we try to say like there's some minimum rho that it has to satisfy. Okay? So the picture I want you to have in your head for that if I have a trajectory here and I have some bowls moving along my trajectory, I think it's completely good if I could just draw in high dimensions. I would draw it like this, moving through time. Right? That's a completely good picture. Okay? But asking for it to be a true Lyapunov function all the way to the trajectory is hard. So what we say is that you should be stabilizing, if you will, to here, but it's okay to be a little sloppy when you're very close to the trajectory. And if you don't leave that out, then some of the numerical issues from the trajectory optimization will actually break the sums of squares request. In the extreme, it's actually, if you just care about getting to the perch, the kind of reachability type statements, you actually don't even need to verify over a whole ring. If you just verified that v of x t equals rho of t implies v dot of x t less than rho dot of t, that would be saying that on the boundary, the rho boundary, I'm at least going in. And it wouldn't, that's like the extreme of that, right? Where it's saying all that I'm actually certifying is that when I'm on the boundary, I'm not leaving the set. And that's actually enough and a numerically easier problem than to certify all the way to the origin. Is that sort of clear? So the time-varying boundary would actually be the boundary of that funnel. And I'm saying when I'm on the boundary, when basically x and t puts me on the boundary of this time-varying function, then I have to be going down into the well. If that's true, then I can never leave the well. It's enough to get finite time invariance. So why is it rho dot here? Right. Certainly I could just choose rho to be a constant, and all the things would hold, and this would just be v dot less than or equal to 0. But it turns out it's a richer specification to allow even my level set to change over time. But to have invariance, then I need to make sure I'm going, if the level set is also changing, I need to be going downhill at least at the rate that the level set value is changing. Yes?
So just to check if I'm understanding things correctly, if we imagine the funnel as a level set of your time varying v.
Yep.
And we say that it's like asymptotically stable, so v dot is negative and v is decreasing as you travel through this funnel.
Yep.
And you start initially inside that level set, like towards, as time progresses, there'll be parts of that funnel which I will never reach given I started inside because I've like gone inwards, right? So
Correct.
in that case, there'll be parts of the funnel which I'm just never going to touch, and those are only relevant if I were to, let's say, start in at that point in those like empty parts of the funnel. Is that
Very nice, right? So if I started here and I had some asymptotic stability, then I would expect the actual rollouts to get sort of smaller and smaller and smaller because that the trajectories that started here would be converging. That's right. That's right. But at the boundary, I mean, so if I had it exactly equal to rho dot, then I could potentially stay directly on there. Yeah. But if I'm strictly less than, I would expect to be decreasing towards the origin in my Lyapunov metric. Exactly right. Yeah.
So if our trajectory doesn't end at a fixed point, sort of once we hit the end of the trajectory, who knows what will happen? But if it does go to a fixed point, is there a nice way to switch to a stabilizing controller once we get there?
Good question. Okay. Yeah. So I said I only talked about, and this goes back to Sava's question actually. So I said this isn't. There's actually nothing about stability properly here. Stability is something that's talking about time going to infinity, and we've only made statements about finite time invariance in that sense. We just said we're going to stay inside this funnel, but we didn't actually say anything about time goes to infinity. So a very natural thing would be to choose the final point of your trajectory as a fixed point, stabilize it with LQR, set your final cost to be the cost to go of the LQR controller, and then it's as if you defined a trajectory from t0 to infinity. And in fact, the funnel from the LQR will catch the output of that finite horizon thing. Right? It would just basically, the last funnel would just be your LQR funnel. Was that clear? I didn't write anything, but yeah. It's very natural to turn this from a finite horizon into an infinite horizon if the end of your trajectory can be a fixed point, a stabilizable fixed point. Right? So for the Cartpole swing up, I would actually call LQR here, take the S there and use that as my final cost. And that's what I did do actually. And then it'll actually be defined as having infinite horizon stability. And that becomes a region of attraction of my time-varying controller. Yes?
If you have something like an airplane or a bicycle where some of the states keep integrating over time, but the rest of it's stable, what do you do for something like that?
Good. So the question is, if you have an airplane or a bicycle or something that has to keep moving to stay in the air, right, or to not tip over, so that they're not going to have fixed points with velocity equal to 0. But there's a natural, they're typically called trim conditions, right? They would be where one of your velocities is constant but non-zero. And there's an easy way to make all the trim conditions look like a fixed point. You tend to just analyze the system without that velocity in there or move the coordinates around that velocity. Moving the coordinates, I think, is better. But there's a simple way to make all this work for airplanes and the like too. Yes?
Is making this, like linearizing around the trajectory, is making that work for limit cycles just like as what you'd expect, like go one half the way around and then do the other half or something and add them together?
Yeah, almost, right? So what we're going to try to find is a periodic S that stabilizes a limit cycle. But there, we're going to really need the transverse stability because most of our walking robots, for instance, are not actually stable in time. If you were to slow them down, they would get behind, and so you would fail the test. If you asked for a time-varying Lyapunov, you have to do that's where the time invariance is. So we'll see that when we get to the walking part. But yes, it's basically we're going to try to make this condition happen, but where the final conditions match the initial conditions so that we loop around and stay in there forever. Cool, okay. So now we have, LQR was already powerful. Now we have a way to do it through space, right? Again, this is so compared to value iteration or some of the other tools we've talked about, this works in high dimensions, right? The trajectory optimization scaled nicely with dimensionality because it's really the discretization only happened in time, not in state. And the LQR, I can solve the Riccati equations in very high dimensional systems. The sums of squares will go less far than the rest of it, but still, much higher than what we can do with value iteration. But we haven't done constraints here. So the other piece that we've been talking about, right, is if you had constraints in your optimization. So we said that there's an extension of LQR to constrained LQR, and we did a linear trajectory optimization to solve that, the MPC. So let's see how that all plays together. Let's kind of do a version of this that handles constraints using the trajectory optimization as our stabilizer. All right, so model predictive control in a little bit more detail. There's just a couple key ideas that make model predictive control fit into that sort of nice framework that we already have. Not all the way. It's actually somewhat limited, okay? But we already talked about this as a generalization for constrained LQR. Okay, but if you want to talk about achieving a goal, stability, these kind of things with a trajectory optimization, then you have to get a couple things right. Okay, so in particular, you remember MPC is the run a trajectory optimization, take the first action, see where I got to, run the trajectory optimization again. It's just repeatedly solving the trajectory optimization. Okay? So to make an argument about the success of that process over time, we need to ensure a couple things. I mentioned this quickly before, but the first thing you need and the most important thing you need is recursive feasibility. Okay? If I solved the trajectory optimization successfully at time 0, that means I found a feasible solution, even an optimal one. Okay, I want to guarantee that when I get to time 1 and I solve another trajectory optimization, I at least get a feasible one. Okay, I need to be recursively feasible. It would be very bad if I solved the trajectory optimization, took one step, and then couldn't solve it anymore and I fell down, right? And there's cases where we can say nice things about recursive feasibility. In fact, there's a simple trick that almost guarantees it, even for very complicated systems. Yes?
Isaac, how does that happen if we establish constraints on those states that we
Good. So, the standard model predictive control thing would be in a receding horizon sort of case. So here's the way I want you to think about it. So you have like time 0 to time n, okay? And at time 0, you're going to optimize, this finite horizon trajectory, okay? At time 1, though, you're going to take that action then, and at time 1, you're going to optimize another trajectory, which is like this, okay? So the optimization problems are almost the same. Like all of the costs and constraints you had in this overlapping interval are the same. So you would imagine if you found a solution to this, you should be in good shape. But there's at least one new set of states and constraints hiding out the back. And there's always a chance that having looked one more step into the future, like if I'm going through life thinking about the next 10 seconds, right, I could go around the corner and be surprised because I wasn't thinking about what happened. I could like run into a wall or something like this, right? Okay, so this is the challenge here, is this, how do you stay recursively feasible even in a receding horizon sort of sense? Okay. Well, since you asked, let me just go ahead and say there's a simple trick, relatively simple trick for doing this. It's the simplest to think about, but it's sometimes a lot to ask, okay? If you were to solve the optimization problem, subject to a final value constraint, x at, let me say if I solve it at, let's say, solve the optimization over times k to k plus n. Okay? Subject to x of k plus n equals x star. Okay? Even if I'm only thinking 10 seconds into the future, if I say at the end of 10 seconds, I'm going to be at a fixed point. Okay? And I'll take the first action, and then I'll move my horizon, and then I'll say at the next time that I'm at least at a fixed point, you know, at time 11, when I'm thinking about it at time 1. And, okay? This is a potentially a lot to ask. You might not be able to get to a fixed point in 10 seconds, but if you can achieve this, then you can easily guarantee recursive feasibility. Okay, so why is that, right? So again, you've lost the first sets of constraints from here. You've gained the new one, but you know the solution you had in the previous problem is valid here, so you've got that feasibility. And if you're at the fixed point, then you know that U0, you know, that you have some solution that's guaranteed to be feasible. Right? More generally, you could just say that I get to some place where I know I have a good control that will get me at least one more step into the future. So when you're like an airplane flying around, it's common to think about, you know, I'm going to dodge the trees, I'm going to whatever, but at the end of my horizon, I'm going to like, especially if you're a small airplane that can prop hang, maybe not if you're a 747, okay, but maybe I'll get to like a safety configuration. And hopefully I'll never have to use that safety configuration. But I'm going to make plans into the future where I know I'll get to the safe state. Because at that place, then I'm always recursively feasible. If I add 1 to the end of the time, then I'll always have a solution, and I can move forward. Now, because that safety configuration is moving arbitrarily far into the future, I will probably never get there. The hope would be I would never get there. But just knowing that I could have gotten there gives me the need to constantly have, you know, satisfies the need to have an optimal solution, a feasible solution.
Is it weird to think about in terms of
Value attrition.
or is it?
So this is where I made a comment before about how discounting in RL, for instance, sometimes offends the control people, right? Because discounting is being very optimistic about the future, but then you can surprise yourself. You get to the future and you're in trouble. So discounting is sort of the opposite philosophy. It's saying I'm going to pretend all is good, and I'll just think about today, right? But this is actually like I'm going to just make sure I have a plan for tomorrow. You know, whatever I do today, as long as I've got a plan for tomorrow, I'm going to keep going. Okay, so that's a simple trick, but in general, the trick I hope you understand is just make sure that you have some pre-canned solution at the one step you're going to add. So for instance, if you could land in the region of attraction of an existing controller that you know, that would also satisfy this, right? If you had some simpler controller, you could do model predictive control for 10 steps and then know that I've got a simple controller and I'm inside its region of attraction. And that would be easier to satisfy. Instead of getting to a point, I could get to a whole region. Okay, but that would give you the same kind of properties. Yes?
It may be a question with not a short answer, but if you're, let's say, flying through a random forest sort of a thing, how can you guarantee that none of the constraints that will come up
good. So the question is, if you're flying through a random forest, how do you guarantee that a tree doesn't appear at your sensing horizon and ruin the day, right?
Or if the safe state is a prop hang, how do you make sure that nothing is too low to be able to come?
Okay, so you would only plan up to your sensor horizon, right? So if you have a laser scanner that sees 30 meters, you don't plan 35 meters, okay? And so you want to make sure, given your current sensing, that that is actually feasible. So there wouldn't be a tree. So by that definition, I would have ruled out the tree. So what would surprise you could be at one time further. But if I'm planning in the things I can see, and I know I'll have a solution that I could stay at forever. Did I say that well enough? Right?
Yeah, I'm just wondering.
It's like I can see a spot to prop hang, right?
Right. I guess I'm just wondering if you can guarantee that exists in advance, or if you have to, at each iteration, find out.
So the statement is recursive feasibility. So it starts with saying I found some plan. At time 0, I had to be successful in finding a plan. I could have prop hanged, right there, and then I could prop hang there, and I'm only moving forward successful prop hangs. So, but if you don't have the first one being feasible, then it's no guarantee. Yes?
I guess, related to this question, it seems like if you wanted to, know that you are recursively feasible through this whole forest, you have to know the whole forest in order to say, I will be recursively feasible through this whole forest.
Well, so I'm trying to avoid that statement. So the question is, so do you have to know the whole forest? I think, so prop hanging is a lousy way to go about life, right? I mean, it takes a lot of energy, and maybe, or I guess landing would be, yeah. If you know you can land, then you don't have to see the whole forest, right? You would, to be successful through the whole forest, you would hope to never execute that safety maneuver. But this is actually saying that no matter what happens, I always have an exit plan. So some new information comes in at the end, but I already had a plan. I know I could have stopped before I hit that new tree I just saw. So it's really trying to be, I don't have to know the whole forest.
So you're doing two things, right? You have your safety net, and then at every time step you are actively solving to figure out the feasibility of reaching some new state.
Yep.
And continue moving around.
Yep.
But if that fails, you just use your
Exactly right.
safety net.
Exactly right. Yeah, so you always have your safety net, which is your last plan that could have been feasible.
But if your goal is completely unreachable, like the goal is in a cave and your plane can't fit into the cave
Yep.
at the end of the forest, then even if you can land your plane, no matter what you do, you'll never be able to reach your goal.
True. Yeah, I didn't say you can do impossible things. I just said that your optimization will continue to find solutions, right? It could be that you wouldn't actually, it might be that finding feasible solutions of the optimization problem might not be enough to make you happy and get your plane into the cave. But it's just saying that you won't violate a constraint.
So it's possible that this doesn't guarantee that you will reach the goal.
That's true. It does not guarantee you reach the goal. I'll show you. There's one more nice thing it can guarantee. Maybe I'll do that now, and then I'll get a couple more questions. Okay. So this is enough actually just to say that my optimization problem will keep having a good day, right? The second thing, if you can say it, is if the cost that you pop in here, if you can guarantee that the cost you're popping in at the new time is only less than or equal to the cost you're taking off at the current time, then you can actually say something about the performance. So this was about constraints, and it just said that the new constraint won't make you infeasible. But there's something about cost, too, okay, which if you say that, I'm going to just go ahead and use the notation I used there. If you can guarantee that x at k, let me say n plus 1, is less than or equal to x at k, right? This is the one that just got dropped. And this is the one that's getting added on the end. Then something kind of cool happens. The cost that you get out of your optimization problem is a Lyapunov function. You know that the cost, you solve the first problem, you get a cost of 5. You know that I'm going to remove one term of the cost, I'm going to add a new term of the cost. I already have a solution. I've got recursive feasibility. I know that my cost is not going to go up. Okay, so for instance, if you ended a fixed point at the nth horizon, and that fixed point had 0 cost, then you could actually guarantee that your initial cost, the first time you solve the problem, is the worst you're going to do. Right? So at time 0, I solved it. It says my cost is going to be 10. Right? I know that I won't get more than 10 even as I move forward in time. My cost, the solution of the trajectory optimization, the value, is a Lyapunov function. I can guarantee the cost. Now, this isn't going to work for your cave, right? Because your cost wouldn't be 0 necessarily at the end if you didn't get to the cave. Okay, so that's really cool. So you can, and it connects this computational object, which is trajectory optimization, and you don't even have it's not like you have our nice, like this is a beautiful Lyapunov function that I can think about and do math with and stuff like this. This is a Lyapunov function that it only exists you can evaluate it at a point by solving an optimization problem. So it's much harder to do sums of squares on this one, for instance. Okay, but it is a Lyapunov function, and it can guarantee the cost if you can certify just those 2 properties. Yeah.
So with this receding horizon approach, is there ever like a trade-off on why you would or wouldn't want to make sort of a longer horizon, or is it just like computational speed?
It can be, so the question is, why not just make that arbitrarily far into the future? I think computation time can be a factor. I think sensing horizon is a real factor too, right? Sometimes I just don't know what's going to happen tomorrow, so I'm only going to plan one day at a time, right? Yeah. There's all kinds of other cool tricks that people do. For instance, like if you're in the MPC world, one of the things people will do is they'll do telescoping time. So you might solve, time 0, time 1, time 2. You could just solve a particular U for every one of those. But then maybe since you're only going to execute the first one, you can have a simpler model where you say, I'm going to just hold U constant from times 5 to 10, and maybe hold U constant from 10 to 20, and then or maybe even logarithmically grow or something like this. So you can think about very long horizons with a limited budget since you're only going to execute the first one. And you can work that in with these kind of arguments too. But yeah, typically there's practical reasons why you can't be all the way thinking to the end. Yes?
If you were worried about like optimization time, if you're trying to do it online, could you solve a small horizon and then use the warm start to solve a bigger, a longer problem?
So good question. Yeah. So this is all about warm starting, right? So the reason you can have these 2 properties is that you know the solution you already gave is feasible. So that's a good warm start. And you know that, especially in a convex optimization, you know that it's only going to get better, right? And if you have a limited computation budget and you can only afford to run 3 steps of your QP, it'll get less better maybe, but it'll still get only better. So it's very compatible with computation limited workflows. It's also interesting. I want to just I'll end with just the slightly hand-wavy thought, but we're using trajectory optimization to stabilize here. Okay, so trajectory optimization to find a path through the forest where the cost function is don't hit a tree, or the constraints are don't hit a tree and get to some goal. That's a hard computational problem. But if you have your cost function is just like this, right? Even if you have a nonlinear optimization, if it's really I've got a pretty good nominal guess and I'm just trying to get back to my nominal guess, that tends to be, even for nonlinear optimization, that's a much easier optimization problem. Think of it as when people do reward shaping or something in RL, right? So having a cost function that says 0 everywhere and then a reward of like 1 when you win the game, that's really hard. But if someone draws the path for you of winning the game and just says, you're a little bit off the optimal path, then that's a much easier optimization, and you can have more. People do in practice use nonlinear optimization even and try to get recursive feasibility kind of statements out of that, right? Because that's a much different optimization.
Does it mean that the cost becomes 0 only when the goal is reached, or is it cost?
That's your choice. You can choose to penalize yourself even if you're at the goal. You could choose, but that's in your design parameters of how you specify the cost function. Cool. Okay. See you next time. We'll post a bunch of. Iterative LQR is doing that repeatedly. I should have said that better. But I hope it's more clear now, all the linearization and everything. We'll post more details and study guides and the like, and answer any questions on Piazza. Yes.
So, just now we saw the funnel, and let's say like the funnel gets bigger.
Yep.
This funnel getting bigger, does that correspond to the lambda max being large?
It's the opposite, right?
It's the opposite, right? Because that was